Hi everyone, this is going to be the first lecture of Chapter 2, and Chapter 2 is going to be covering chemistry, and Chapter 2 is also going to be broken into several lectures, whereas Chapter 1 we only had 2 lectures. Chapter 2 we're going to have several lectures covering the content here. And this first lecture is going to be relatively brief compared to what we've had so far. But before we dive into Chapter 2 and start talking about chemistry, let's have our not really attendance review questions. A patient is lying in bed with their back to you. They're lying on their left side with their head to your left and their feet to your right. Their sternum, which is the hard bone in the middle of the chest, is blank to their navel. The stomach belongs to which level of structural organization? And when you get cold and shiver, what is the effector? And related to that, what type of feedback loop is this an example of? So try to answer these questions on your own before listening to see what the correct answers are. Use this as a chance to practice to see, are you caught up on the material? Are you understanding everything? Are you retaining it well? Okay, so hopefully you've done that. Now let's go ahead and see what the correct answers are. So we have a patient here. When you walk in the room, their back is to you. They're lying on their left side. Their head is to your left. Their feet are to your right. So based on this, answer the following question. Their sternum, which is that hard bone in the middle of the chest, is blank to their navel. Well, let me see if I could draw on this screen here. When you walk in, basically what you see is this. They're lying on a bed. This is the back of their head that you're seeing. But it doesn't matter what position the patient is in, right? Remember, no matter what, the patient is in anatomical position. Their arm should be a little bit lower there, but that gets the point across. And you are facing the patient, so you can see their face there. And based on anatomical position, the sternum is above their navel, but what do we use for the word above? The sternum is superior to the navel. All right, so it doesn't matter what position the patient is in. You always refer to the patient as if they are in anatomical position. And in anatomical position, the sternum is superior to the navel. What if I had said, instead of the navel, the sternum is blank to the heart? The sternum is, we can answer that a couple of different ways. Well, the sternum is in front of the heart, so the word for that is anterior. The sternum is anterior to the heart. But also the sternum is closer to the surface of the body, so the sternum is superficial to the heart. Either of those words would work just fine there. All right, next question. The stomach belongs to which level of structural organization? Remember, the levels of structural organization were things like atoms, molecules, organelles, all the way up through organism. And the stomach is an organ, so it belongs to the organ level of structural organization. When you get cold and shiver, what is the effector? Well, when you're shivering, it's your skeletal muscles that are contracting and relaxing really, really quickly, and they're doing that so that they can generate heat. So in that description, skeletal muscle is the effector. And what type of feedback loop is this an example of? Remember, that is a negative feedback loop. Most of the feedback loops in the body are negative, and that just means that the outcome is opposite from the original stimulus. The original stimulus here was cold, and we shiver to warm up. So the outcome is the opposite. Okay, so now we're going to go ahead and start covering Chapter 2, Chemistry. And I know from experience that this is a topic that students really, really do not like. They struggle with it, but the reason that they struggle with it is because they panic when they think about chemistry, and they convince themselves that they can't do it. They shut their brain off and they go into panic mode. Now, before we ever start talking about chemistry, I want to tell you, I also hate chemistry. We do not have to go really, really deep into chemistry. And since I hate it, and since it's not going to require really, really deep understanding, I'm only going to give you the chemistry that you need to have. So the chemistry that we talk about, you do have to understand it. But I'm going to make it as straightforward as I can. Don't let your brain shut off. Just learn it at the level that we teach it here, and you'll do just fine. So this is just going to be a really, really basic introduction today. And then in our next lecture, we will start going a little bit deeper. And that will take probably another 3 or 4 lectures after this one. Now, let's talk about matter. Matter is a word that we've all heard, and we kind of think we have a good understanding of what it is, but if I ask you to define matter, the majority of people can't because they don't really know how to put it into words. But when it comes down to it, matter, the definition is just anything that occupies space and has mass. If something takes up space and has mass, then it is matter. Everything is made of matter. Now, right now, if you look around the room or wherever you happen to be, we can see things like walls and tables and the computer that's in front of you. Those all are taking up space and they have mass. So they are made of matter. But some other things that we may not really easily think of. The air that's in the room. We can't see it, but it's there. It takes up space. And even though it doesn't have a lot of mass, it does have mass. So even the air itself is matter. And when we talk about matter, there are 3 states of matter. And now I want to tell you, there's going to be several times in this chapter when something that I say is absolutely not true. There are not 3 states of matter. There are, depending on which chemist you talk to, there are roughly 12 or more states of matter. But for our class, we are only going to consider the 3 that are most common. We are going to talk about the ones that you learned in elementary school, and that is solid, liquid, and gas. But these are also going to have some definitions. And we all, if I asked you to point to a solid, every one of you can do it. But if I asked you what's the definition of a solid, that's another one of those things that's a little bit trickier than most people think. So let's give some definitions to solid, liquid, and gas. First, solid. Solids are matter that has a very defined size or volume and a very defined shape. So most of you right now probably have a pencil or a pen in your hand. That pencil or pen is a solid. It has a definite shape. It has a definite volume or size. I'm going to use the word volume and size interchangeably here. I'll just use size most of the time because it's easier to say. But when I say size, just think volume. That pencil or pen has a definite size and a definite shape. If it's in your hand, If you lay it on the table, if you throw it through the air, wherever you put it, it's got the same size and the same shape. That is a solid, something that has a definite size or defined size and a definite shape or a defined shape. Now, that on its own can still be a little bit confusing. So let's look at the other two states of matter and see what makes them different from solids. Liquids also have a defined volume or size. Liquids have a defined volume, but they take the shape of the container that they are in. Liquids have a defined volume, but their shape changes based on their container. So let's say you go to the fridge and you grab a jug of milk. And that milk, let's say it's almost empty. There is a certain volume of milk in that container, but it's shaped so that it's basically taking on the shape of that container. It's probably not filling the whole thing if it's almost out, but the shape is filling that portion of the container. And now let's take that milk and pour it into a glass. Well, now in that glass, there's the same volume of milk, but it's got a completely different shape because now it's in a different container. And you get ready to go take a drink and you drop it, and the glass hits the floor and all of the milk runs out. There is still the same volume of milk, but it's changed shape because now it's in a different container. Now it's in the room, which is the container. Finally, let's look at gas. Gases do not have a defined volume or shape. Their volume and shape both change to fill the container that they are in. A gas, its shape and volume change to fill the container that it is in. So earlier, I said look around the room and you can't see the air, but it's there. Well, that air is a gas, and it is completely filling the room that you are in. Now, there are certain machines that can create a vacuum by pulling the air out of something. So let's just imagine there is one of those machines hooked to the room that you're in. And we turn that machine on and suck all of the air out of the room. Well, that air has to go somewhere. So that air, we could potentially put it in a small mason jar. Now that air, that gas that had been in your room, filling the entire size and shape of your room, is instead filling the size and shape of that mason jar. Now let's say we take that mason jar and break it. Well, now that gas is going to escape and it will attempt to fill the size and shape of whatever room it's in. So solids have a defined volume and shape. Liquids have a defined volume, but they change their shape to fit the container. And gases do not have a defined shape or volume. They instead fill the volume and shape of the container that they're in. Now let's change gears, move away from matter. Now let's talk about energy. And this is another one of those words that most of us can kind of get an idea of what energy is, but we couldn't really define it. And unfortunately, this is another word kind of like a few lectures ago when we talked about theory. And most of the time, when someone uses the word theory, they're using it wrong. Energy is another one of those words that really gets misused a lot. So energy, by definition, is the capacity or the ability to do work. That is all that energy means. The capacity or ability to do work. Now, a lot of times you will hear somebody talking about, oh, they're giving off a bad energy, or these crystals radiate energy, or something like that. No, they don't, because that doesn't even mean anything. Energy is the capacity or ability to do work. And when we talk about energy, now we're going to get into some tricky wording. This slide and the next slide are going to have two words that seem like they don't really have much difference between them. So let's see what they are. Type. Energy comes in two types: kinetic energy and potential energy. These are the types of energy. Keep that in mind, because on the next slide we're going to look at something that seems like it means the same thing, but it doesn't. Kinetic energy is stored energy. I'm sorry. No, it's not. Kinetic energy is moving energy. Completely disregard that first sentence that I said. Kinetic energy is moving energy. Potential energy is stored energy. And we can convert between the two. Let me write this out, so in case there was any confusion, I apologize for that. Kinetic is movement, potential is stored, and we can convert between the two types. So there's lots of different examples. So let's give one example. Let's say there is a hill, and there is a ball at the top of the hill with a wedge in front of it. Well, right now, that ball has potential energy. The ball has potential energy. What does that mean? Well, that ball has the potential to do some work. It has the potential to roll down that hill. But it's not rolling down the hill because that wedge is in the way. Now let's see what happens if I get rid of that wedge. If I get rid of that wedge, what's going to happen? The ball is going to roll down the hill, and as it rolls down the hill, it's releasing that energy. It's moving. It's converting the potential energy into the kinetic energy. It's changing the stored energy when it was at the top of the hill into movement as it rolls down the hill. So we converted between the two types. So now keep that in mind. We're talking types. Types, the energy is either stored or it is moving. Now we're going to talk about forms of energy. Before we were talking about types of energy, now we are talking about forms of energy. And I know that sounds really, really nitpicky, but those two words mean something different. Type versus form. So let's look at the different forms that energy can come in. And each of these can be either type that we just mentioned. Chemical energy is the energy stored in chemical bonds. Later in this chapter, in one of the upcoming lectures, we're going to talk about chemical bonds. When certain elements are joined together, let's just draw an imaginary atom joined to an imaginary atom. There is a bond between them. There is chemical energy in that bond. Well, if it is stored, what could we call that? That is potential chemical energy. There is energy stored in that bond. What happens if we break that bond? Well, there's going to be some energy released if we break that bond. So let's say we break that bond, it's going to give off some sort of energy because we have converted from potential to kinetic chemical energy. And chances are when we break that bond, we're actually even going to convert to a different form of energy. It's in all likelihood not going to be chemical. It's going to be something else. So we can, again, convert between types of energy. And I'm alluding to the fact that we can convert between forms of energy. But there is both potential and kinetic for all of these. Let's look next at electrical energy. Electrical energy is the movement of charged particles. So electrical energy, an example of that could be a battery. Battery stores electrical energy. When we hook that battery by way of a wire to something, then those charged particles can start to move. So that is kinetic electrical energy. Next, mechanical energy. This is what we drew on the previous slide. It's directly involved in the movement of matter, so that ball at the top of the hill is potential mechanical energy, and as that ball rolls down the hill, it's converted to kinetic mechanical energy. And finally, radiant or electromagnetic energy. And this is energy that travels in waves, such as light that we can see, or heat that we can feel. And we saw that energy can be converted between types. We can also convert from one form to another. And when we convert it, some of it is lost as heat because it's inefficient. So it looks like some of that energy is going away. But there is an important rule that energy cannot be created and it cannot be destroyed. So let's see exactly what that might mean. Here's an old-fashioned light bulb. There's still some of these around. We are getting better at making light bulbs. But let's see what this means. I take a light bulb and I hook it to an electrical current. So there's a wire coming along and electricity is passing through it. So that is electrical energy passing into this light bulb. And that electricity passes through the filament. And as it passes through the filament, that electricity is converted to light. So light is given off. But if you've ever taken one of these old light bulbs while it was plugged in and tried to unscrew it, you've probably noticed that light bulb gets really hot. Or if you just hold your hand near it, or if you sit too close to an old light bulb, you can feel the heat coming off of it. So we also get heat. Where is that heat coming from? Well, when we convert from electrical energy into radiant energy, light, it's inefficient. Some of that conversion is lost as heat. So as we convert from electricity to light, heat is being given off. And that's why that light bulb gets hot. When you exercise, you are converting from chemical energy to movement. So we're converting from chemical energy to mechanical energy. And as we are converting, what happens when you exercise? You get hot because energy is lost as heat. Anytime we convert from one to another, some of that is lost as heat, but none of it is being created and none of it is being destroyed. It's just converting from one form to another. Now we're going to change gears again and talk about elements. All matter is composed of elements. There are roughly, I think, about 118 elements that we know of so far, give or take. And each of those elements has a unique set of physical properties and a unique set of chemical properties. No two elements are exactly the same. And I've got some examples of elements down here. We've got a diamond, which represents carbon. We've got this gas inside the container, which represents chlorine. I've got the only liquid at room temperature metal down here, which is mercury. Now, in your book, near the back in, I think it's Appendix C, there is a periodic table. We'll look at a periodic table here in just a moment. I want to first ease any stress that you may have and tell you, you do not need to know the periodic table. A lot of the items on the periodic table you're going to pick up just because we talk about them quite a bit, but you do not need to memorize any of it. And anytime I ask you something about the periodic table, I will give it to you if it's on an exam or a quiz, or you'll have access to it in your textbook if it's on homework. So you will always have access to the periodic table. Now let's see, what do we mean by chemical properties and physical properties? So physical properties are things that you can observe without changing the substance. What does that mean? Well, things like color, appearance, odor, its melting point or boiling point, its density, things like that. Because we can measure all of those without changing the thing that we're looking at. Chemical properties, though, those are properties that describe how a substance changes into another substance. Now, that does not mean that carbon is going to change into mercury. That's not something that happens. These are things that, how does it react with other substances? So things like flammability, corrosion, reactivity, heat of combustion, things like that. Those are chemical properties because we are changing the substance into another substance. Well, now let's put everything that we've talked about so far together. Remember, matter was anything that takes up space and has mass. And all matter is composed of elements. Well, we take up space and have mass, so that means we are matter. And if we are matter, then we are composed of elements. So what are we composed of? This chart is in your textbook on, let me see, it's on page 41 of your textbook. And you do not need to know this chart. What I do want you to know are the 6 major elements that compose the human body. All of these others, it's good to know that they are in our body. You do not need to know what percent any of them make. You do not need to know what do they do, although you will figure a lot of that out over the course of the semester. But I do want you to know the 6 major elements that make up 98.5% of our body mass are oxygen, which makes up 65%. Don't worry about that 65. Carbon, which makes up 18%. Hydrogen makes up 10%. Nitrogen, 3%. Calcium, 1.5%. And phosphorus, 1%. So I want you to know the names of these elements. Don't worry about the percentage. These 6 elements make up the vast majority of our body weight. They are the major elements that our body is made of. These other elements, don't worry about knowing, okay, lesser elements. Don't worry about knowing, okay, trace elements. But you will, just because we talk about them a lot, learn about things like potassium and sodium, chlorine and iron. Now, all elements are composed of atoms, or all elements are atoms. And atoms, by definition, are the smallest unit of an element. So if we were to take, let's just say, oxygen. I have a lot of oxygen in a container, and I take half of that oxygen. Well, it's gotten smaller, but it's still oxygen. And then I take half of that. Still oxygen. And I take half of that. It's still oxygen. I could keep taking less and less and less and less, and it's still going to be oxygen. But at some point, if I have the right machinery, I could get down to 2 oxygen atoms, take one of them away. Now I still have an oxygen atom, but I can't go any smaller than that and still have oxygen. The atom is the smallest unit of an element. So if I did go smaller, because there are things smaller than an atom, and we will look at them. There are things smaller than an atom. But if I go smaller than an atom, it no longer has the same properties of the element that it had previously been. If I take an oxygen atom and break it apart, I no longer have oxygen. So there's a lot of different ways to represent an atom in picture form. Here's 2 ways. I will show you some other ways. What we see here is a helium atom. And over on the left, this is called the planetary model. And it's called that because right in the middle, we have something called the nucleus of the atom. And then going around it, we have rings where we have little structures called electrons. We'll come back to that in a moment. It's called the planetary model because it's kind of like the solar system, with the sun in the middle and planets going around it. Over here, we still have a helium atom, but this is called the orbital model. And in the orbital model, we still have the nucleus in the middle, but the electrons are kind of fuzzy because they're constantly just kind of vibrating and moving around. So instead of drawing them in this ring, we just kind of draw a cloud around the nucleus. When I draw a helium atom, and I recommend you do the same because it will start to get messy, and I'll show you why in a moment. The way I draw it is I will draw He to represent helium, and I will draw something similar to what we see right here with this ring and the 2 electrons in it. I'll show you why I draw it that way in a moment, but I will tell you it's basically to keep things neat because it will get really, really messy if you start trying to draw some bigger atoms. So I draw a variation of the planetary model. Now let's look at the things that an atom is made of. I just said that there are things smaller than an atom. They just no longer have the properties of the element. So here in the middle, we have the nucleus. The nucleus is the middle or the core of an atom. And in the nucleus, we find 2 different things. We find protons. Protons have a positive charge, so sometimes we just write P plus for a proton. And we find neutrons. Neutrons don't have a charge, so sometimes we will write N with a 0 next to it. So protons and neutrons are found in the nucleus. Protons have a positive charge, and neutrons have no charge. So real quick, let's think about that. Protons and neutrons are in the nucleus of the atom. Protons have a positive charge and neutrons have no charge. What can you tell me about the nucleus of an atom? See if you can think of what we can say about the nucleus of an atom based on that information. What is positive plus nothing? Remember, protons have positive, neutrons have no charge. Positive plus nothing is positive. So a nucleus of an atom has a positive charge, always. The nucleus of an atom has a positive charge. Now, going around the nucleus of an atom are these small structures called electrons. Electrons have a negative charge, so sometimes they're written E with a minus sign next to it. And electrons, since we're talking about the planetary model, they travel in these rings called orbitals or shells. Orbitals or shells. I like to use the word shell. So these electrons are on this shell going around the nucleus. Now, electrons have negative charges, so the shell is negative. Now, in its natural state, and we will learn about that next lecture, in its natural state, the number of protons is equal to the number of electrons. In an atom, in its natural state, the number of protons is equal to the number of electrons. Well, we said the nucleus is positive. What can we say about the atom? If the number of protons and electrons is equal, then an atom has no charge. It is neutral because the positives and the negatives cancel each other out. So that's a helium atom. Let's look at what happens when we start building. Well, if we look at our periodic table, and you can pull your periodic table out of your textbook in Appendix C. If we look at our periodic table, we have helium in the top right, but we also have carbon. Here is carbon, which is a little to the left and down from helium. The further we go to the right, or the further we go down the periodic table, we're getting bigger. We're adding things to the atom. So carbon has a little bit more going on than helium. We can see that there are more things going on in the nucleus, and we can see that we have added some rings. We've added some of those shells. Now, your book, for whatever reason, calls them energy levels. I don't like that term, and I hope that you don't get used to using that term, because it's better to call these shells. So this is the first shell, this is the second shell. Each one of these shells can only hold a certain number of electrons. The first shell can hold up to 2 electrons. The second shell can hold up to 8 electrons. and every shell after that can hold up to 8 electrons. Now that's another one of those things that, remember I said I'm going to tell you some stuff that is not true in this chapter? If you go on to take higher level chemistry classes, you will see that these shells can actually hold more than 8 electrons. For our class, we will only ever talk about these shells having 8 electrons, so that's what we're going to say. The first shell can hold 2 electrons, the second shell, and every shell after that can hold up to 8 electrons. And we only add another shell if the previous shell is full. All right, we only add another shell if the previous shell is full. So here we see in helium, we have 2 electrons. If we needed to add a third electron, we would have to add another shell. Here in carbon, we have 2 in the first, 4 in the second. In nitrogen, we have 2 in the first, 5 in the second, and we could keep adding more electrons until we get to 8. If we needed to add another electron, then we would again add another shell. Sodium has 2 in the first shell, 8 in the second shell, and 1 in the third shell. And this third shell also could hold up to 8 electrons. The first can hold 2, the second and everyone after that can hold 8. Now, let's look at the periodic table. This is the same periodic table that's in your book, although it's got a little bit different color and some different numbering schemes on it. But every periodic table is the same with just some minor formatting differences. Now, this periodic table is the one that I will give you for exams. So you will have access to this if you need it on an exam. And I like this one that came from a different textbook just because of the way that it does some coloring. And the reason is, in biology, all of these yellow things and all of these gray things, we really don't talk about in biology, so we can ignore them. We can say, look at the purple and we're good. And in all honesty, if we look at the top 4 rows of purple, we're good. Beyond this 4th row, biology really doesn't have anything to do with these guys. All right? So let's do some drawing based on what we can see in this image. I'm going to go on and move to another slide, but I suggest either having your textbook open to this page or printing this out so that you have access to it while we do some drawings. All right, so first, let's look at the top left on that periodic table. And what you will see is a box with an H in it, with a 1 at the top, and with 1.0079 at the bottom. Now, let's first learn what all of these different things mean, and then we're going to kind of do some drawing based on what that box tells us. This top number here, this number is called the atomic number. In the middle, there will be a 1 or 2 letter symbol called the atomic symbol. And at the bottom is another number called the atomic mass. Some books will call it the atomic weight, although weight is not the proper term. Atomic mass, or the mass number, sometimes you will hear it called, is the bottom number. So let's see what each of these things actually tell us. The atomic symbol, the 1 or 2 letter abbreviation in the middle, that is how we can write the name of the element. It's kind of like shorthand or just an abbreviation. Most of the time, it's the first letter or the first 2 letters of the name of the element. H, atomic number 1, is hydrogen. Hydrogen is atomic number 1. We saw a moment ago helium, He, was atomic number 2. And a lot of the times they follow something like that. But now and then we will get something like atomic number 11, which is sodium. And if you look on your periodic table, atomic number 11, sodium, what's its atomic symbol? Na. Well, that's because sometimes they use the Greek or Latin words for these. So they won't always be the actual first or first 2 letters of the English name. Now, I will not ever ask you to memorize the atomic symbol for the elements. You will pick some of them up because we will talk about them a lot this semester. By the end of the semester, I guarantee you will know that sodium is Na and potassium is K because we're going to talk about them so much. All right, at the top is the atomic number. Now, the atomic number tells us 2 things. One, the atomic number is just the order that we put these on the periodic table. It's for organization purposes. But much more important than that, the atomic number tells us the number of protons. The atomic number is the number of protons. So hydrogen has 1 proton because it is atomic number 1. But let's go even deeper. The atomic number, the number of protons, well, the number of protons defines the element. The definition of hydrogen is an atom that only has 1 proton. The definition of hydrogen is an atom that only has 1 proton. If we found an element somewhere, it doesn't matter where, anywhere in all of the universe, and we didn't know what it was, and we looked and it only had 1 proton, by definition, it is hydrogen. We've just identified it. And if we find hydrogen anywhere in the universe, if we checked, we would see that it has 1 and only 1 proton. So the atomic number is the number of protons, and the number of protons is the definition of that element. Now let's look down at the bottom, the atomic mass. Well, the atomic mass, even if we don't see that it is rounded, we will always round it to the nearest whole number. So 1.0079, I'm going to round that to 1. Sometimes you'll round it up, sometimes you'll round it down. You're just going to round it to the nearest whole number. So the atomic mass is equal to the number of protons plus the number of neutrons. The atomic mass is equal to the number of protons plus the number of neutrons. All right, so if the atomic number tells us the number of protons, and the atomic mass tells us the number of protons plus the number of neutrons, if H is hydrogen, and hydrogen has atomic number 1 and atomic mass 1, how many protons does hydrogen have? Well, by definition, it has 1 proton. And that's what we have written over here. How many neutrons does hydrogen have? Well, how do you find neutrons? You can find neutrons by taking the atomic mass minus the atomic number. Well, the mass is 1, the number is 1, so the number of neutrons is 0. Did you see how I did that? The atomic mass minus the atomic number. So mass minus number is neutrons. Hydrogen, most of the time, has 0 neutrons. How many electrons does it have? Well, we just said on the previous slide, in its natural state, the number of protons is equal to the number of electrons. So how many electrons does it have? 1. We have 1 proton, 0 neutrons, and 1 electron. Now, the number of protons is constant. You do not change the number of protons in an element, because if you change the number of protons, it turns it into a different element. And in its natural state, however many protons it has the same number of electrons. But neutrons can change. Some hydrogen has 0. Most hydrogen has 0 neutrons. Some hydrogen has 1. Some hydrogen has 2. So that's why this bottom number was not a whole number. It was 1.0079. But most hydrogen has 0 neutrons. Now, let me clear the screen here. And we're going to do one more drawing before we move on. We're going to draw, let's say we're going to draw potassium. And as I'm erasing this, go ahead and look at your periodic table. Find potassium, which is atomic number 19, and see if you could draw everything that we just drew for hydrogen. Potassium, atomic number 19, atomic mass 39. I'm going to let you draw that, and go ahead and pause this video so that you can see if you could draw it and then check it against what we draw here together. Well, first let's draw an atom of potassium. All right, and now you're going to see, remember earlier when I drew the hydrogen atom on the previous slide? I'm going to show you why I draw it the way that I do. If I was going to draw the nucleus of a potassium, how many protons would I draw? Well, I would have to draw 19 protons. And how many neutrons would I have to draw? Well, what's 39 minus 19? 20. I would have to draw 19 protons and 20 neutrons, and that would get really messy, really crowded. So instead, I just draw a K and say that's the nucleus. The neutrons aren't really going to be all that relevant, so I don't draw them at all. And what's the definition of potassium? The definition of potassium is 19 protons. So by drawing a K, potassium, that's the exact same thing as drawing 19 protons. So Now, if I have 19 protons and I have 20 neutrons that I'm not even going to bother drawing, how many electrons do I have? In its natural state, there are the same number of electrons as protons. So 19 protons, 19 electrons. Now that we know that, let's go ahead and draw the rest of the atom. Well, we have K to represent the protons. Now we have to draw 19 electrons. We draw our first shell. The first shell, remember, can hold up to 2 electrons, but we have a lot more to go. So we have to add a second shell. The second shell can have how many? It can have up to 8. All right, so now how many electrons have I drawn? I've drawn 10. I still have 9 more to go. So I have to add a third shell. Go ahead and add in the electrons. How many electrons can the third shell hold? 8. Well, now I've got 18 electrons drawn, but I need to draw 19. So what do? I add a fourth shell and put an electron in that. So that is potassium. A K to represent 19 protons and 20 electrons in the middle. 19 protons and 20 neutrons in the middle. And then I have to draw my electrons in all of these shells. 2 in the first, 8 in the second, I still need more. So 8 in the third, I still need more. 1 in the fourth. So that's 19 electrons. And that's how we draw potassium. Now, let's go back to our periodic table for a moment, and let me show you some kind of shortcuts of things that we can look at this periodic table, even if we don't know that much about the elements, something that we can look at to get a basic idea of what the atom would look like. There's a lot of numbers on this table. Well, first thing we're going to do to reduce it is ignore the yellow and ignore the gray. We're biologists, so we don't need to know about those right now. Just look at the purple. We've already learned at the top of each box is what? The atomic number, the number of protons. At the bottom of each box is the atomic mass, the number of protons plus neutrons. But there's some other numbers here if we look at the purple boxes. There's these Roman numerals going across the top, and there's these Arabic numbers going down the side. Let's look at the Roman numerals first. All right? 1, 2, 3, 4, 5, 6, 7, 8. Those numbers tell us how many electrons are in the outer shell. Whatever the farthest out shell is, these numbers tell us how many electrons are in that outermost shell. Now, let's go back and look. Potassium. How many electrons are in the outermost shell? Right there. There is 1. If we look at the periodic table, find potassium. It's right there. It is in column 1. That 1 tells us everything in this column only has 1 electron in the outermost shell. And right there it is. Everything in column 2 has 2 electrons in the outermost shell. 3, 4, 5, 6, 7, 8. That's how many electrons are in the outermost shell for everything in each of these columns. So it sounds like the outermost shell is special, and it is. The outermost shell is called the valence shell. The valence shell Now, in our next lecture, we are going to talk a lot about the valence shell. But by definition, the valence shell is just the outermost shell of electrons. Keep that word in mind. We'll talk about it next lecture. Now, if we go down the side, these numbers tell us how many shells are there. Up here at the top, hydrogen and helium, they only have one shell. Everything in the second row has two shells. Everything in this third row has three. Everything in the fourth row has four. Well, there's potassium. Let's go and double check that. One shell, two shell, three shell, four shell. And in the fourth shell, which is the valence shell, how many electrons are there? One. So we can use the layout to tell us how many shells are there and how many electrons are in the valence shell. How many shells? How many electrons are in the valence shell? Now, we've talked about protons and electrons a lot. Protons define the atom, tell us which element we're talking about. Electrons, the number of electrons is equal to the number of protons in its natural state. But we said neutrons, there can be different numbers of neutrons. Hydrogen could have 0, it could have 1, it could have 2. Well, when we change the number of neutrons, we're not really changing too much about the element. If we change the number of protons, we change the entire identity of that element. If we add a proton to hydrogen, it becomes helium. Then changing neutrons doesn't seem to have much effect. It doesn't change what element we're talking about. So here's a word that we will learn called isotopes. And isotopes are kind of weird. And luckily, after today, you'll never deal with them again. I will not talk about them anymore after today. But if you are going into radiography, medical imaging, you will unfortunately talk a lot about isotopes. And you will get that in your chemistry and physics classes. You won't need to know anything more about it for biology, so we won't talk about them. So what are they? They are the same element, but with different numbers of neutrons. So hydrogen with one neutron, or hydrogen with 2 neutrons, or hydrogen with 0 neutrons. They're all hydrogen, they just have different numbers of neutrons. Sometimes you will hear them maybe in a chemistry or a physics class given other names. Actually, in our textbook on page 43, it gives you the names. I won't ask you the names. But sometimes you will hear them called hydrogen, deuterium, and tritium. They're all 3 hydrogen. The only difference is they have a different number of neutrons. So let's close out this lecture with a thinking cap question. Based on what we just said, isotopes have different numbers of neutrons, but they are the same element. What would be the same among isotopes? And what would be different among isotopes? So if we have hydrogen with 0 neutrons, hydrogen with 1 neutron, and hydrogen with 2 neutrons, what would be the same? Well, we would have the same name, we would have the same atomic symbol, H, we would have the same atomic number, 1, which is the same as the number of protons, 1, the same number of electrons, 1. Well, what would be different among hydrogen with 0 neutrons, 1 neutron, or 2 neutrons? Well, obviously the number of neutrons would be different, but also the atomic mass would be different. Hydrogen with 3 neutrons would have a greater mass than hydrogen with 0 neutrons. Okay, so that's going to wrap up today's lecture. Next lecture, we're going to move on and start talking about how do atoms interact with each other. So first, make sure you understand everything that we presented today because it lays the groundwork for our upcoming lectures. All right, I will talk to you in the next lecture.